Hello students, so today in this lecture I will tell you the protection of carbonyl compounds as acyclic and cyclic acetals ketals. In my previous lecture I told you the protection of alcohols, diols, triols, and they were also protected by converting it into the cyclic or acyclic acetals ketals. So these are the, we can say, for alcohols and for carbonyl compounds they are vice versa. Protection is the same way, we can do the protection the same way. So let's summarize how we can protect these carbonyl compounds, and let's summarize in the form of this table. So protection of this carbonyl compound in the form of or as reagent used and deprotecting agent. So first of all we will see the acyclic one, then we will see for the cyclic. So acyclic acetals ketals. And so suppose if we have any carbonyl compound, then that can be converted into acyclic acetals ketals. So this is carbonyl compound, so after reacting it with alcohol, that can be converted into this acyclic or acyclic acetals or ketals. So this is OR, again this is OR. So this is the acetals, this is ketal, and suppose here this R is equal to H, then that would be the acetal. Now how can we get this? So this can be, we can get it by reacting the carbonyl compound with any alcohol. Suppose if we have a 2 molecule of this alcohol, so this in presence of acid, so acid as a catalyst, that can be used. Okay. So here the deprotecting agent, this is the deprotecting agent used is, we can do the acidic hydrolysis for this deprotection. Okay, so acidic hydrolysis of this acetals give you the this carbonyl compound and this alcohol. Okay. So either we can use this any acid as a catalyst, or some Lewis acids can also be used, or we can say Lewis acids can be used, like we may use as a ZnCl2 zinc chloride or titanium chloride, titanium tetrafluoride, it can be used, or boron trifluoride can also be used as this catalyst. Okay. Now, so this is one of the way when we react the carbonyl compound with the alcohol. Okay. Or another way, we can convert this carbonyl compound into acyclic acetals and ketals by reacting it with, this is one of the way, or we can react it with some orthoesters. Suppose if we have an orthoester, so this orthoester in presence of this acid as a catalyst, this can also give you the acetals and ketals, because reaction of this orthoester in presence of this acid, it gives 2 molecule of this, gives 2 molecule of alcohol again, and then that will react with the carbonyl compound. So orthoester, so this is our orthoester. So this orthoester in presence of this acid catalyst give 2 molecule of, we can write this, give 2 molecule of alcohol. Okay. And that can also be deprotected in a similar way, that is the acid catalyst. So this is one of the way, and another as a cyclic one, as a cyclic acetals, ketals. Okay, so one of the ways by converting this into 1,3-dioxolane. So if we have any carbonyl compound, then this carbonyl compound, if we have this carbonyl compound, then that can be converted into 1,3-dioxolane. So this is our 1,3-dioxolane, 5-membered this cyclic acetal. This is 1,3-dioxolane. And how can we get it? We can get it by converting it into, by reacting the carbonyl compound with any diol. So if we have any diol in presence of some acid catalyst, so this will give you this 1,3-dioxolane. So this is one of here, or some, suppose some catalyst, that is Lewis acid, BF3 boron trifluoride ethylate can also be used. Okay, so now this is one of the way, or we can convert this carbonyl compound into the 1,3-dioxane. 1,3-dioxane we can convert. So for this we can convert this carbonyl compound into 6-membered ring. This is our 6-membered ring. Means carbonyl compound can be converted into 1,3-dioxane. So how can we convert it? By using triol. By using triol we can convert it in acid catalyst. Okay. So here we can use the acid hydrolysis for the deproduction. Okay. Now next one, third one, if we see, we can convert it into the cyclic dithiocetals ketals. Okay. So cyclic or acyclic. First, let's see this acyclic dithiocetals ketals. Okay. So if we have any carbonyl compound, then that carbonyl compound can be converted into thioacetals. Thioacetals, in place of this oxygen, we will take the sulfur only. So sulfur, so this is our dithiocetals ketals. So to get it, just in place of alcohol, we can take a thiol. So if we take a thiol, then we can get thioacetals. Okay. In the same way, we can convert the carbonyl compound into cyclic dithiocetals ketals. So let's see. Cyclic dithiocetals ketals. So one of the way, if you see, then that can be in a similar way. It can be converted into 1,3-dithiolane. It can be converted into 1,3-dithiolane, or it may be converted into 1,3-dithione by converting into 1,3-dithiene. Okay, so the structure is similar, just change oxygen into sulfur. So the structure will be similar to that one. This is our 5-membered thiolane, and thiene, it is 6-membered. It is 6-membered, like this. Okay. So what we should take the reagent in place of this diol we can take a thiol. So we may take a thiol here, or acid catalyst may be used. Acid catalyst, suppose we may use the either H plus can be used, or in place of this we can use some other acid catalyst also. So suppose in place of this we can use suppose this. Same way. Okay. Thanks. Now, for the deproduction of this dithioacetals and ketals, so we should remember that it can be deprotected by using a mercury salt. It can be deprotected by using the mercury salt. So, if we take HgCl2 in H2, either this can be taken, or this is one of the deprotecting agent. It can also be deprotected by taking sodium periodate. Okay. Or we can deprotect it in presence iodine, DMSO. We can also take this iodine DMSO and this aqueous, this methanol. We can deprotect it by using these. So these are some of the deprotecting agent for this thioacetals and ketals. Okay, so now this 1,3-diol. So in place of this these acidic catalyst, we may use the other thing also. Suppose the cyclic, this carbonyl compound, it can be converted into this 1,3-dioxolane by using, and suppose if we use a TMS, and this in presence of TMS triplet. Okay, so we can convert the carbonyl compound into 1,3-dioxolane by taking this one and this TMS triplet as a catalyst. This may be taken as a catalyst. So we will see the mechanism of these one by one. Let's see the mechanism. Okay, so first of all we will see for acyclic acetals and ketals. So let's see for acyclic now. So if we have any carbonyl compound, so this carbonyl compound, how we can convert it into acyclic acetal ketal? By reacting this carbonyl compound with a alcohol. So first of all, in presence of some acid catalyst. So in presence of this acid catalyst, first of all this carbonyl compound, this is protonated, this oxygen is protonated to generate a strong electrophilic center at this carbon. And now if we have a alcohol molecule, so this alcohol being nucleophile, it will attack a strong electrophilic center here, and we will get a OH, and this is okay. So in next step is proton transfer. Okay. Now, so this will again in presence of second molecule of this ROH alcohol. So this will attack over here, and this H2O being a leaving group, it will leave out, and we will get here minus H. Acid catalyst, it will be removed, and we will get the this acetals or ketal. Okay, so this reaction is a reversible one. This reaction is reversible one. So this is our protection. So this is protection, and now in the same way, if we see the reverse one, then we can deprotect it. Suppose if we deprotection, we have acetal or ketal in presence of acid. So acid hydrolysis, we should do the acid hydrolysis for the deprotection. This will be protonated. And in next step, this alcohol being a leaving group, it will leave out. Okay, and what we will have? So now this H2O as a nucleophile will attack this electrophilic center. As positive charge, it will neutralized. Again, second molecule of alcohol, that is removed. So first molecule of alcohol is removed. Now second molecule of alcohol, this is removed, and we will get a ketone. So like this, the ketone, that is carbonyl compound, is deprotected. Okay. Now, so in the same way, what I told you, we may use in place of this alcohol, two molecules of alcohol, we may use the orthoesters also. So let's see if we are using orthoester. Suppose if we are using orthoester in place of alcohol, then what would be the mechanism? So suppose if we have a orthoester, and this in presence of acid catalyst. So one of this that will be protonated. Okay. Now this one of the alcohol, it is removed over here. So one of the alcohol is removed. Suppose this methanol, one of the methanol molecules is removed, and it will act for the protection of this carbonate molecule. So one of the alcohol molecules is removed, and in next step, okay, so okay, and now again this proton transfer. Okay, so here this another molecule of this alcohol is removed. So this is one of the molecule of alcohol which is removed. This is the another molecule of alcohol which is removed. So it will protect this carbonyl compound to form a acetal or ketal. So we will have a okay, so like this. So this is the mechanism for converting this orthoesters into the two molecule of this alcohols that will act as a protection for this carbonyl compounds. Okay, so let's see for the cyclic acetal ketals now. Let's see the mechanism for cyclic acetal and ketals. Second one, cyclic acetals ketals. Okay, so if we have this alcohol, if we have a carbonyl compound, then that may be treated with diol. So first of all, this is protonated, and then we have a suppose diol. So let's first write this one. So positive charge over here, and now we can diol, it will act as a nucleophile and it will attack this electrophilic center. Positive charge is neutralized and we have this OH and OH. Okay, now in next step, proton transfer. So this is the mechanism to convert this carbonyl compound into the cyclic acetal or ketal. Okay. In the same way, this can be deprotected. So this is also a reversible one. These reactions are reversible. Okay. Now, if you want to deprotect it, suppose let's see for deprotection. So we have acid hydrolysis that can be done, and we have this oxygen. One of this oxygen, this is protonated, and now in next step, so this bond that will broken, and Okay. Now again in next step, the proton transfer. Removal of this acid catalyst, and we have this carbonyl. So like this. So in this way, the cyclic acetal ketals can be formed. So that can also be used some other like if we use in place of this one diol, we may use this OTMS and as a and this triplet. TMS triplet can also be used. Okay, so suppose if we have a TMS triplet, that is trimethylsilyl, trifluorosulfonate. Okay, trimethylsilyl trifluoromethane sulfonate. Okay, so this is the trimethylsilyl trifluoromethane sulfonate. So this acts as a catalyst. Okay, this acts as a catalyst. So suppose if we have a carbonyl, and this carbonyl in presence of, so this will, and we have suppose trimethylsilyl trifluoromethane sulfonate. So if you see, then trimethylsilyl, okay, trifluorosulfonate. So this is now this is a good leaving group. This OTF is being a good leaving group, and this will act as a catalyst. So it will act as a catalyst. So here this will attack over the silicon in the d orbital, and this molecule will leave out. Okay, so this TMS, this is a TMS group. Okay, so this is a TMS group. So what we can get, we may get here OTMS. Okay, we may get here OTMS. So positive charge goes here, and this is our negative charge. So in next step, and finally this will undergo cyclization. So this TMS group that will be removed by this OTF group. So this OTF that will remove this, suppose if we have OTF, and finally this will get cyclized, and TMS group that will be removed, and it will get cyclized to give the cyclic acetals. Okay, so like this. So this is for protection and deprotection of cyclic acetals and ketals. Now we can see for the thioacetals and ketals. So in